Hello. Today I want to talk to you about two different types of energy calculations. The first are energy calculations related to constant pressure calorimetry, and the second are energy calculations related to the change of phase or state of a type of matter. Both of these sets of calculations alone won't make a whole lot of sense. But in the context of the material covered in Chapter 6, the thermochemistry chapter in your textbook, they do play an important role. I'm choosing to discuss these two types of calculations in detail because they are calculations with lots of steps that students often perform incorrectly. Calorimetry itself is a process that is used to study the change in enthalpy of a chemical reaction. Now, because we are not going to isolate our chemical reaction in a closed, completely sealed system, the type of calorimetry we're actually addressing here is constant pressure calorimetry, where we assume that constant pressure is not from the non-changing atmospheric pressure around the reaction. The reason we have to use calorimetry to measure the change in enthalpy of a reaction is because we cannot measure the enthalpy of an individual reactant or an individual product. Therefore, we measure the change when we react the reactants with the products. So we measure the change for the reaction process. The other problem we have is that in order to measure a change in energy, we actually have to be able to stick a thermometer inside of a system. Unfortunately, molecules are too small to stick a thermometer inside of them. Therefore, when we measure the energy change or enthalpy change for reaction, what we are actually going to measure is the energy of the surroundings. And we will use our knowledge of system and surroundings to interpret or infer from our measurement what happened in the system. In this case, we're going to put a reaction in aqueous solution so that we can measure what happens to the temperature of the solution, which is part of the surroundings, when certain things react. There's a lot of different calorimeters that exist out there, but you can make a pretty simple one out of some household supplies. There's one shown on the left side of your screen that is made out of 2 coffee cups, a cork stopper style lid, and a thermometer with a stir stick in the middle of it. Anybody can make one of these. You'll get a chance to use one in lab. Mathematically, what we're really talking about here is measuring the heat released or absorbed by the system. So we're going to use that equation Q equals M, which is the mass, times specific heat times delta T. But as I stated a few moments ago, what we're actually going to measure is Q for the solution, and what we actually want to know is Q for the reaction. In this case, the reaction is the system, and the solution is the surroundings. So what we say is that Q reaction is actually minus Q solution, because energy given off by the reaction will be absorbed by the system, and vice versa. So we need that negative sign to account for the difference in energy flow in terms of being released or absorbed. Now, Q solution is actually the mass of the solution times the specific heat of the solution times delta T of the solution. And we can measure all three of those things for the solution, so we can calculate Q solution. We can take the negative of Q solution to get Q reaction. Now, there's a difference between Q reaction and enthalpy. And that difference is a factor known as the moles of reaction. The easy way to get moles of reaction is simply to calculate the moles of the limiting reactant in the process and divide Q reaction by those moles to get delta H. This is probably best illustrated by an example, so let's look at one. Let's presume that we want to mix 50 milliliters of 0.1 molar silver nitrate with 50 milliliters of 0.1 molar hydrochloric acid in a constant pressure calorimeter. If we do this and the temperature of the solution increases from 22.30 degrees Celsius to 23.11 degrees Celsius as a result of the reaction, the question is, what is the enthalpy change for the reaction in kilojoules per mole? In order to perform this calculation, it is going to be necessary for us to assume that the density of the solution is 1.000 grams per milliliter, and its specific heat is 4.184 joules per gram degree Celsius. In other words, this is a dilute solution, so we're going to assume it has the same density and specific heat as liquid water. The first thing we're going to want to know about this particular problem is what reaction is actually occurring here. In this case, it is the reaction of silver nitrate with HCl to produce solid silver chloride and nitric acid. The balanced equation for that reaction indicates that both reactants have a ratio of 1 to 1, and both products have a ratio of 1 to 1. In other words, there are no non-1 coefficients. That'll become important in a minute. The second thing that we need to do is calculate Q solution. To calculate Q solution, we need the mass, the specific heat, and the delta T. To calculate the mass of solution, we must convert the volume of solution to the mass using density. Before we can calculate the mass of solution and using the density, however, we need the total volume of solution. In other words, we're going to take 50 milliliters of AgNO3 plus 50 milliliters of hydrochloric acid. We're going to get a total volume of 100 milliliters. 100 milliliters times 1.000 grams per milliliter, in other words, times the density, tells us that our solution has a total mass of 100 grams. We also need to calculate our delta T. When you calculate delta T, which is the change in temperature, you always take the final temperature minus the initial temperature. In this case, that's 23.11 degrees Celsius minus 22.30 degrees Celsius, or 0.81 degrees Celsius. Now we're ready to calculate Q solution and Q reaction. Q reaction is minus Q solution. Q solution is mass of solution times specific heat of the solution times delta T. In other words, Q reaction is minus 100 grams of solution times 4.184 joules per gram degree Celsius times 0.18 degrees Celsius, 0.81 degrees Celsius, sorry. And if you multiply that together, you get a total of negative 340 joules. Notice we round our answer to two significant figures because of the two significant figures in our delta T. Well, negative 340 joules is negative 0.34 kilojoules. In order to get from Q reaction to delta H for the reaction, we need to talk about the moles and calculate the moles of the limiting reagent. If you look at the equation, you note that HCl and AgNO3 have a 1-to-1 ratio. This is helpful because that means that whichever of the two reagents has the smaller number of moles will be the limiting reactant. In this case, both reagents have the same molarity and volume, meaning they have an equal number of moles. So neither HCl nor AgNO3 are limiting, which means we can calculate the moles of either reagent here and use them to determine delta H. In this case, I have chosen to calculate the moles of AgNO3. Moles of AgNO3 is equal to 0.0500 liters, in other words, 50 milliliters turned into liters, times 0.100 molar, which gives us a total number of moles of AgNO3 of 0.00500 moles, or 5.00 times 10 to the minus 3 moles of AgNO3. To calculate delta H, we now need to take negative 0.34 kilojoules divided by 0.00500 moles. When you do that, you get an answer of negative 68 kilojoules per mole. Here's what that means. For every mole of reaction that occurs, 68 kilojoules of energy is released. You can perform similar calculations using a calorimeter with different reactions. You'll see several examples of this in Chapter 6 in your textbook. Now I want to turn our attention to the material covered in Chapter 11, Section 11.6 and 11.7, which deals with the energy of the various changes of state or phase of a particular substance. For example, let's consider water. Water could be solid ice. If it thaws or melts, it becomes liquid water. That is an endothermic process, or a process that requires energy. Another process that requires energy is the process that turns a liquid into a gas, known as vaporization. The opposite of vaporization, an exothermic process, is condensation. And the opposite of melting, also an exothermic process, is freezing. There is also the process of sublimation, which is endothermic. That is transitioning directly from a solid to a gas. And its opposite, deposition, which is an exothermic process transitioning directly from a gas to a solid. We're going to ignore sublimation and deposition in this discussion and instead talk about the individual phase changes going from solid to liquid to gas and vice versa. The energy associated with a change of a solid to a liquid, or with its melting, is known as the heat of fusion, or delta H fuse. The energy associated with vaporization is known as the delta H of vaporization. This, of course, is the transition from a liquid to a gas. For a particular substance, its delta H of vaporization is always larger than its delta H of fusion, for reasons that will be discussed in later sections of this course. For any substance, one can draw a heating curve like the one on your screen. You'll notice that heating curve essentially is a graph. On the y-axis is increasing temperature, and on the x-axis is heat added, or probably more correctly, energy added. You'll notice that the line of the graph proceeds in sort of a stair-step fashion. And you'll notice that there are 5 distinct segments to that line. 3 of them appear on an angle. In other words, in those 3 sections within the 3 phases of matter, solid, liquid, and gas, you notice that as energy is added, the temperature increases. This makes perfect sense if we think about it. We put energy into a substance, we do expect its temperature to go up. Think about a microwave, for example. The other 2 segments of the line, however, provide some interesting discussion. You'll notice that they do not show an increase in temperature as energy is added. And in these 2 plateaus, we see that matter is transitioning from one state to another. In the lower plateau, we have melting occurring. In other words, we are transitioning from the left side of the plateau to a solid at the melting point to the right side of the plateau as a liquid at the melting point. And in the upper plateau, you notice that the boiling point is where that second plateau occurs. Now we are transitioning from purely a liquid at the boiling point on the left side to a gas at the boiling point on the right side. For each segment of this line, of which there are 5, one can calculate the energy change that a substance must go through to transition through that segment. There are actually 2 types of equations that you're going to use for these 5 segments. If the temperature is changing, in other words, the diagonal lines or those within one state, you'll use the Q equals mc delta T equation. The only catch here is you have to be very careful to make sure that you're using the specific heat of the substance for its appropriate phase. Solid water and liquid water, for example, have different specific heats. The second type of an equation is similar to the first, except it's used on the plateaus, and the variation in the equation occurs depending on which plateau you are on. If you were talking about the lower plateau where we're talking about the solid to liquid transition, you're going to use the equation Q equals N times delta H of fusion. If you're on the upper plateau where we're talking about the transition from liquid to gas, you're going to use Q equals N times delta H of vaporization, where N is now the number of moles of the substance. So we transition from a mass to a number of moles. Notice there is no delta T term, because delta T on these plateaus is 0. The energy being put in is only causing the phase of the substance to change. Let's illustrate this with the use of these heating and cooling, this heating curve with an example. And let's calculate the amount of energy required to go through several phase changes of one substance. So let's look specifically at how much energy in kilojoules is required to convert 1.00 moles of ice at minus 25 Celsius to steam, or vapor, or gas, at 125 degrees Celsius. The specific heat of ice, liquid water, and steam are 2.09 joules per gram degree Celsius, 4.184 joules per gram degree Celsius, and 2.01 joules per gram degree Celsius, respectively. The heat of fusion of water is 6.02 kilojoules per mole, and the heat of vaporization of water is 40.7 kilojoules per mole. We're going to carry out this calculation in 5 segments. One calculation for each segment of the graph we saw on the previous slide. And then to get the total energy, we're going to add those 5 answers together at the end. Because the question asks for the answer in kilojoules, we'll have to make sure also that all 5 of our answers from each segment are in kilojoules so that we can add them together at the end. Let's start with segment 1. In segment 1, we are heating ice, 1 mole of ice to be specific, from minus 25 degrees Celsius to its melting point at 0 Celsius. Because there is an increase in temperature here, we will use the Q equals mc delta T equation. 1 mole of ice, then we must convert to grams, and the molar mass of water is 18, so 1 mole of ice is 18.0 grams of ice. The specific heat of ice is 2.09 joules per gram degree Celsius, and the delta T for this process, final minus initial temperature, 0 minus a minus 25, is 25 degrees Celsius. Plugging these things into the Q equals mc delta T equation, you get 941 joules, if you round to 3 significant figures, and dividing by 1,000 to convert joules to kilojoules, you get 0.941 kilojoules of energy, which is required to convert 1 mole of ice at minus 25 degrees Celsius to ice at 0 degrees Celsius. For segment 2, now we're going to convert the ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. Note there is no temperature change here. This is strictly melting. So now we're going to use the equation Q equals N times the heat of fusion. N in this case being 1.00 moles of ice. The heat of fusion of ice, 6.02 kilojoules per mole. 1 times 6.02 is 6.02 kilojoules of energy that is required to convert 1 mole of ice at 0 degrees to 1 mole of liquid water at 0 degrees. Now we're going to look at segment 3, which is the energy required to heat 1 mole of water from 0 degrees Celsius up to its boiling point, which is 100 degrees Celsius. In this case, again, 1 mole of water is 18.0 grams. Specific heat of liquid water now is required, which is 4.184 joules per gram degree Celsius. And the delta T is the final temperature, 100 Celsius, minus the initial temperature, 0 Celsius, or 100 degrees C. Plugging these values into the Q equals MC delta T equation, since we do have a change in temperature here, we get 7.53 times 10 to the third joules, or 7.53 kilojoules of energy that is required to raise the temperature of 1 mole of water from 0 degrees to 100 degrees Celsius. Now we transition to segment 4, which is vaporizing water to steam. We're going to boil 1 mole of water at 100 degrees Celsius. We're going to change it entirely from a liquid at 100 degrees Celsius to entirely a gas at 100 degrees Celsius. There is no delta T, so we need the Q equals N times the heat of vaporization equation. N in this case still remains 1.00 moles. The delta H of vaporization as given in the problem is 40.7 kilojoules per mole. 1 times 40.7 kilojoules per mole gives us 40.7 kilojoules. And finally, we need to calculate the energy required to heat the steam, 1 mole of steam, from 100 degrees C to 125 degrees C. Again, because there's a delta T, we're going to use the Q equals mass times specific heat times delta T equation. And in that equation, 1.00 moles of steam is 18.0 grams. Specific heat of steam is 2.01 joules per mole or gram, same thing, degrees Celsius. Delta T is 125 degrees C minus 100 degrees C is 25 degrees C. So 18.0 grams times 2.01 joules per gram degree Celsius times 25.0 degrees Celsius is 905 joules, rounded to 3 significant figures, and 905 joules is 0.905 kilojoules. To get the total energy involved, we're now going to take Q1 plus Q2 plus Q3 plus Q4 plus Q5. In other words, the Q values from each of the 5 segments. 0.941 plus 6.02 plus 7.53 plus 40.7 plus 0.905 equals 56.1 kilojoules. 56.1 kilojoules of energy is required to convert 1 mole of ice at minus 25 degrees Celsius to 1 mole of steam at 125 degrees Celsius. It is usually helpful for these phase change type problems if you sketch the heating and cooling curve, marking clearly the point at which you start and the ending point, which will tell you how many different equations that are necessary. If the substance is not water, it's also important that in the problem you are supplied with the melting and boiling point of the substance. If not, it's hard to sketch that heating and cooling curve. Additionally, of course, you'd have to be given the heat of fusion, heat of vaporization, and various specific heats. These problems mathematically are not challenging. However, figuring out which number goes where and remembering to carry out all steps carefully and accurately can be a challenge, much like the problems that involve calorimetry. Practicing both of these problems is strongly encouraged.